Hello guys, I'm GT and let's continue with numerical integration part 4, Composite Simpson's 1/3 rule today. So here is Composite Simpson's 1/3 rule, and as we have said in the last video, if it's a simple Simpson's 1/3 rule, the n is equals to 2 and you use quadratic function to determine the approximate area under curve. Okay, A to B is a range and M is a midpoint. So what we're gonna talk about today is we put it n times. So basically for a range of A to B, we divide it into n segments, or you can say n sub-intervals. And these n sub-intervals have a range of x1, x2 to xn plus 1. And this n can only be even, which is n equals to 2, 4, 6 and so on. Okay, so the distance between the x, the consecutive x, we call it delta x. It is the same for all intervals. So delta x is equals to b minus a over n. As we have n intervals here, so we just divide the distance of b minus a into n sub-intervals. So you got this. Okay, so the higher the n, the lower the delta x, which means the lower the difference with actual area and the approximate area under curve, and therefore the accuracy increase. Okay, so let's prove Composite Simpson's 1/3 rule today. As you can see here, we got yesterday we proved simple Simpson's 1/3 rule, which is a 1, 4, 1, right? Let's do a recap here. If you got a Simpson's 1/3 rule, the A, M, B, the approximate A is equals to this. Okay, you can see that the coefficients for the functions is 1, 4, 1. So now we got n sub-intervals, right? So you divide the n sub-intervals into two pairs. The two consecutive pairs where you got x1 here, x2, x3, x4. This is called as sub-interval, okay? So you group two sub-intervals into a pair, you got what we got in a simple case. So we have proved that in a simple case, the coefficient of a function fx n is 1, 4, 1. So in this case, we divide the n into two pairs, two pairs, two pairs. We got 1, 4, 1, 1, 4, 1, 1, 4, 1. As you can see here, 1, 4, 1, 1, 4, 1, 1, 4, 1, 1, 4, 1, 1, 4, 1. So now you just plus up the coefficient. You got the coefficient as 1, 4, 2, 4, 2, 4, 2, dot, 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 4, 2, 2, 4, 1. Okay, so how can we express this as a general equation? So this is what I said just now. You divide the n into two pairs, two pairs, two pairs. So the first term in each pair is called fx 2j minus 2, and then 2j minus 1, 2j. So it's 1, 4, 1. So if you sum it up, you will get the thing of 1, 4, 2, 4, 2, 4, 2, which ends up with 4, 1. So you can see here, this is what we got, the general formula. It is not hard to memorize this, as you can see there's a pattern 1, 4, 2, 4, 2, 4, 2, 4, 1. You just need to remember that it ends up with 4, and then remember the magic number 1, 4, 1. So if you forget the sequence, you just writing it down like this, and then you add it up. So you got 1, 4, 2, 4, 2, 4, 2, dot, 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 2, 4, 1. So just remember 1, 4, 1, the magic number. Okay, so let's do an easy example. So if you're given a function and the limits, use Composite Simpson's rule to determine the area under curve. while n is equals to 4. So the first step is you need to find delta x. So you just sub in the values, you got x equals to 1 over 2. And then just use a formula, delta x divided by 3, and then sub in the 1, 4, 2, 4, 2, 4, 2. You got this. And then in this case, you just sub in the values according to the fx. So what is the fx here? Fx here is this. So fx equals to x squared. So you just sub in when x equals to 0, 0.5, 1, 1.5, 2. So you got it is 2.667. But note that the x squared here is a degree of 2. So the answer is exact, and if you want to prove this, you just do a simple integration. You will find that it is also 2.667. So we can make a conclusion that when it is a degree of 2 polynomial, this method is exact. So remember 1 for 1, the magic number. Thank you for watching. If you guys would like to see more math and engineering mathematics videos in the future, hit the subscribe button. See you guys next time.